Good evening, everyone. Today we want to look at important subject, analysis of variance. Short, the acronym is ANOVA. Now we discuss comparison of two means when we talk about t-test, where we compare two means. Another way is an association between a categorical exposure and quantitative outcome. Of course, for the mean, the exposure categorical, there are only two categories. But in a situation where you still want to do categorical exposure and outcome, which is quantitative, and you have more than two categories, can be three categories, can be four categories. For example, now you want to compare the weight of people, three set of people, people that you prescribe exercise, people that you prescribe diet, and the people that maybe you didn't prescribe anything, placebo, control. In that situation, so there are three categories of people. We want to compare the mean weight among the three. So you cannot actually use t-test to compare more than two means. And the reason we'll discuss it, because that is what leads to analysis of variance, a way of going around it, since one cannot use t-test to compare means of more than two groups. So when you have means of more than two groups, three groups, four groups, as many as possible, how do you go about it? You use analysis of variance. So let's first of all, as an introduction, just go through some overview. So when you compare means, so in comparison of means, you can compare two means. You can compare more than two means. So this first one now is a t-test we have done before. This one just a reminder. It's the same logic. When you see observed difference minus expected over estimate or standard error. So when we talk about independent sample mean t-test, if you look at the formula, when we talk about dependent mean, look at the formula. But that's for when you are talking of two means. But when you have more than two means, you use ANOVA. ANOVA means analysis of variance. ANOVA is a group of statistical methods employed to compare means of three or more groups, not of more or more groups. It's good to understand the t-tests are not used to compare means of more than two groups. Therefore, it is good to have an understanding of the reason and because of the concept of family-wise error rate. Because of that family-wise error, that is why we cannot use t-test to compare more than two means. So let's talk about this family-wise error. If you remember, I'm sure you are familiar with this, even when we're talking about, what do I call it? Probability distribution. When you talk about binomial distribution, we have something like this. But this one is for combination. In how many ways can you combine n number of things in high number of ways? For example, you want to pair. Pair now means you want to arrange them two by two. And you have three things, A, B, C. Let's say you have three things. In how many ways can you pair the three things? So NC is the number of the possible ways you can do that, which is the combination. N is the number of items. Unit of combination, since we say pair, mean two. So, of course, if it is two things, it's only one way you can compare two things now. A and B, just one. But when you have up to three, A, B, C, you have A, B, C. We are talking about maybe three means now, A, B, C. In that many ways. So if N is the number of groups, K to be paired, So R is 2 because you say you want to pair. That is, you want to move them 2 by 2. That's why R is 2. So the number of combination is K. K factorial. K factorial means if you say 5 factorial, it means 5 times 4 times 3 times 2 times 1. If you say 4 factorial, it means 4 times 3 times 2 times 1. So K factorial divided by 2 into K minus 2. Can you see now? Because you say N minus R times R. So you know we are pairing. So R here is 2. N is the K, and the K is what you see as N up there. So K 2 into K minus 2. So if you look at the family-wise error is equal to, so in this situation, you can see that how many times can you pair it? You do it. 3 times 3 times 2, 6 over 2 times 3 minus 1 to make it 2. So making 3. 6 over 2 making 3. There are 3 ways you can pair it. Now, family-wise error here is 1 minus, you reject your null hypothesis at 0.05. So the remaining one will be 0.95, which is the confidence level. So the error will be 1 minus 0.95 raised to power 3, because we say how many ways can we combine? 3 for this situation, let's say 3. C is the number of tests you want to carry out. That's the number where you can come. So it's very simple. Even let's you say when you have A, B, C, 3 groups, you can say A and B and combine it and compare. You can say A and C. You can say B and C. Those are the possible 3 ways to combine, to pair 3 things. If there are 4, A, B, C, D, A and B, A and C, A and D, and B and C, B and D, and C and D. Can you see now? These ways you can pair 4 groups. If there are 5 groups now, you go to see that 10 ways. 10 ways. That shows that when you have 3 groups, if you want to pair them, to do 2 tests for each of them, because 3 tests can only use for 2. So if you do 2 tests, that shows that if there are 3 groups, you have to do 3 tests. If there are 4 groups, you have to do 6 tests. If there are 5 groups, you have to do 10 tests. So as the number increases like that, the number of 10 and the number of this thing increases. This table is just to show you the different ways you can, different combination you can have. For example, number of K. If there are 2 groups, you see now, you can only have 1 pair. If there are the second line, if there are 3 groups, you have already established it, is 3. If there are 4 groups, 6. If there are 5 groups, 10. If there are 6 groups, 15. 7 groups, 21 tests. If there are 8 groups, 28 tests. If there are 9 groups, 36 tests. If there are 10 groups, you can combine, pair it in 45 ways, 45 tests. Can you imagine? So for each of the tests now, let's look at the, if you let's look at the family-wise error. If you put the p-value 1 minus 0.09 and 0.95 raised to power number of tests. So if it is 1 test, of course, your p-value is what you 0.05 you have set. So if there are 3 tests, can you see now, is 40.3%, 0.13, 0.143. That's where you reject null hypothesis. If there are 4, can you see 0.265? Can you see? Whereas originally what you set is 5%, level of significance 0.05. See, as the number of tests increases, what it just means in the plain language is that when you do too many tests, the probability that at least one or two will be significant is very high, even by chance, even though when there is nothing, no association per se, the probability that of some being significant is high. It's more like gambling. You're like someone that doesn't know much, know anything. If you continue writing exam they don't relent. One day will pass. The pass does not mean he knows anything. Because he has been doing the exam, just gambling, it now become like gambling. Eventually it will pass. It's the same thing. So when you do several tests, the probability that you're going to see one that will be significant when in natural sense there's nothing significant, so it's very high. So because of that, instead of doing t-tests, the intelligent people now came and now invented this method, analysis of variance. So what they call the analysis of variance is the variance they analyze. Here now they didn't, it's a way of comparing the means anyway, but indirectly compare the means by analyzing the variance. So ANOVA also called F-test. Tell us whether 3 or more means are the same or not. It produces F statistic, which is similar to the T statistic anyway, in that it compares the amount of systematic variance in the data to the amount of unsystematic variance. What I mean by this is, I have already told you that the numerator for a statistical test is this difference you are looking at. The denominator is the measure of inherent difference, variability, even apart from the difference you are looking at, the natural difference, variability, which most of the time is measured by the standard error. So it is when the difference you are looking at, if it's significant, it is when the difference is so big, because when you make it as numerator, when it is so big, far bigger than the inherent variability, that you can actually say there's a difference. And that is why it has to be bigger than 1, not just greater than 1, because if something is numerator, if it's bigger, it should be greater than 1, not just greater by 1. It's going to be high, the value will be high. So to the extent that it will reach a critical point, and I say, oh, this difference is not due to difference, it's not due to chance. So the probability of it due to chance is very slim, very small. So that's the logic. Even the ANOVA is the same thing. So you measure what you're going to see as the numerator is the difference you are looking at, the variability you are observing in the data set. You want to compare it with inherent, the internal variability in the data. F is the ratio of model to error. We'll talk about it. It is also called, you understand the meaning of this model or error. It is also called F-test to reflect the name of the person that developed the technique. It was developed by Fisher, Sarona Fisher. When you hear of Fisher's test, F-test, all these Fisher. Fisher was the person that, when there was no computer in those days, was very that compiled the statistical table. The man was a genetics, so very intelligent person. Those are the giant in the statistics. That's why we keep on saying that the biologists like you that develop statistics over the year. Let's look at the theory of this ANOVA. The ANOVA examines the variation across all groups at once, using concept of variation between groups. Instead of you pairing it like if you want to use theta, like 2, 2, 2, all of them, even if there are 5 groups, no matter the number of groups, you observe the variation at once. So what it compares is that it compares the variation between the different groups as the numerator, and the variation within the group, each of the group. You can see between, let's say 3 groups now, A, B, C, what is the variation? What's the difference between them? is the one that serves as the numerator. But what are the difference within each group? The variation within each group, within, that is the inherent variability within. So that within will be the denominator rather, while the between will be the numerator. We expect if the variation between which we are trying to see that is very significant is far higher, what you're going to get will be far greater than 1, since that is the numerator. If there is no difference between the group, then the ratio of the variance between the group and within the group will be 1, since the variation will be the same. What we are saying is that if the variation between the group is equal to the variation within the group, your statistic will be 1 now, because it's only 1 you get when you divide something of the same unit. 50 divided by 50, it gives you 1. 1 million divided by 1 million, it gives you 1. Since the numerator and denominator are the same, it gives you 1. Variation between group divided by variation within group, it will be 1 if there is no difference in the variation between and within. If the group means are different per se, then variation between group divided by the variation within group will be greater than 1. Yes, it will be greater than 1. So ANOVA is an omnibus test. The meaning of omnibus is a test that just tests everything at the same time. It's a big, when you say something, all omnibus means everything. Tests everything at the same time. It tests for an overall effect, or if there is or are any different or differences among all the group. Let me explain. It does not provide information about where the difference lies. You have 3 groups now. You say, oh, there's a difference in these 3 groups. But it will not tell you where is the difference. Is it between A and B that is different, or between A and C, or between B and C? Because when you say there are 3 groups, you can say, you see that the A is greater than B, less than A, or what? So where the difference lies, I don't know. It does not tell you that. It just tell you that there's a difference. If there's no difference anywhere, it will tell you, rest your case. But if there's a difference, there are things we do, we see as we discuss. There are several ways in which means can differ. Look at it. All the 3 means are significantly different. If all of them are different, 1 and 2 and 3, all of them are different. That should have bar x1 is not equal to bar x2, is not equal to bar x3. The means of group 1 and 2, if they are the same, but group 3 are significantly different. So you can say bar x1 is equal to bar x2, not equal to bar x3. If the means of group 2 and 3 are the same, but group 1 has significant difference. So it means that bar x1 is not equal to bar x2, but bar x2 is equal to bar x3. If the means of group 1 and 3 are the same, but the group 2 has significantly different means, it means that bar x1 is not equal to bar x2, is not equal to, sorry, it's equal to bar x3, but it's not equal to bar x2. Let's look at that. Because most of the time, without an example, let's look at it. See a very simple example. It is the example that will give you understanding of it, because no matter what you talk, it will just be in the realm of what is this saying, what is this saying. Now let's look at example. Let's look at the video score of 3 group of participants with different interventions. So we have 3 groups, 15 of them, but they are grouped into 5, 5, 5, into 3. So they were giving different doses of Viagra, sildenafil citrate, for performance. Let's say the first group was given placebo, in the sense that there's no active ingredient there, just like shock. The group 2 was given low dose Viagra, that's sildenafil citrate, low dose, not maybe 1 tablet or whatever. While group 3, each of them was given high dose, maybe 2 tab. So you can see we have two. So all those people, 5 people in group 1, they were given placebo. They were not actually given anything, just like chalk. Then group 2 were given low dose Viagra, while group 3 were given high dose. And they rated their libido on the rating scale of 1 to 10 for them to rate. It is that will rate themselves anyway. How do you feel? You have to put this thing on the scale of 1 to 10. So how they got the results is not our problem. It's how to analyze it. So look at the score. Group 1, the 5 of them won't get 3, score 3. You remember group 1 are the ones that they were not given anything. Group 1, we have 3, someone scored 2, someone scored 1, another one 1, another one 4. And the average for group 1, when you divide all these things and divide by 5, because there are 5 of them, give you 2.2. And the standard deviation, if you calculate it, is 1.3. Then group 2, so one got 5, another one 2, another one 4, another one 2, 3. So when you calculate the average is 3.2, and the variance, the standard deviation rather, is 1.3. So mind you, for both of them, the standard deviation 1.3, the variance 1.7. You know, standard deviation, the variance is square of standard deviation. So if you say 1.3 times 1.3, give you 1.7. That's what is there. And if you find the square root of 1.7, you give you 1.3. Then group 3 rather. Someone scores 7, another one 4, 5, 3, 6, 5. 6. So when you calculate the average is 5, and the standard deviation is 1.58, and the variance 2.5. So there are no way you see some other thing grant me. For each of this group now, we have a mean for each group. Because there are 15 number. Because there are 15 number, you can actually add all the 15 together and calculate the mean. That would be grand mean, the mean of all of them, grand mean. So it will give you 3.467, and the standard deviation, grand standard deviation will be 1.767, variance 3.124. Another way of getting that grand mean, you can actually add all the 3 mean together and divide by 3. To still give you the same grand mean as if you added all the 15 together and divide by 3. Now, let's see the way to work. If you look at this, is what explains the analysis of variance. See, they have calculated the variance there, calculate the standard deviation. But let's look at the meaning of analysis of variance. This analysis of variance, there are 3 levels of variances that are in the data. 3 levels of variances. Or let me go back to the table. There are 3 levels of variances. You see now, for each group, you can calculate the mean and standard deviation and variance. So each group now, so that is the variance in each group is what we call variance within group. Within group. That's a level of variance. In each group has its own variance. Now, I told you also that you can actually add all the 3 means together and calculate the grand mean, overall mean, and calculate the standard deviation of each, that is, the variation of each of the mean from the grand mean. So that variation at that level, the variance at that level is what we call variance between group. You know, the first level is the one within each of the group, variance within group. You know that for each of the group now, they have their own standard deviation, mean, standard deviation. But we can, each of those three means, because there are three number, you can add it together and divide by 3 to get the grand mean and calculate their deviation, variance from the grand mean. So that type of variance, the variance within, is showing the variability between the different groups. You know, the first one was variability within each of the group. But this second one is variability or variance between groups. That is the second level of variance. There is a third level of variance, which is actually the total variance. You know, I said the other time, you can actually calculate that grand mean by adding all the 15. You know, separate them into groups. Just add everything together and calculate the mean. And now calculate the variance. You can deviation of each of the value of the 15 on the grand mean. That level of variance of variability is the total variability in that data. Can you see now? So we have variability within group, right? Then variability between group, then the total variability. So something you are going to see is that this total variability is actually the addition of the variability within and variability between. Let's look at it, explain it very well. So the first column, so this thing I did when one day, one of these years, where I went to Port Harcourt to do this training on statistics, I was explaining variance. I was struggling, people, they didn't understand. So, and now when I retired to my hotel room that night, I began to crack my brain. How would I do to explain? Because I have explained many other things, other topic we treated. Okay, but this when we go to this ANOVA, they find it difficult to understand. And now it was in the night, in the hotel room, I was thinking, brainstorming, thinking, how do I explain? And I use Excel. Something just came to my mind. And I use Excel to generate this. And the following day, when I got back to the workshop, I explained, everybody just got it. And from that time, I just leave it. That's what, for you to understand it, this is what will make you conceptualize it. Now, the first column is like the serial number because there are 15 of them, but they are arranged according to group. If you look at the second column, is the group. So what I did was that the first one to 5 are the one in group 1. Then the group 2 is number 6 to 10. Group 3, number 11 to 15. For that data set, we just look at it now. So if you look at the third column, that is the value of the libido of each person, arranged like that. So look at number 4 column. That number 4 column is the, you know, when you can calculate, you know, we have already calculated before, which is already here also. If you had all the 5 for each group together, calculate their mean. You already know that for group 1 is 2.2, for group 3, for group 2 is 3.2, for group 3, which is iDose, 5. So now that column 4, what it does is to look at variability within each group. That is, it removes each mean from the original value. From 1 to 5 now, it removes 2.2, which is the mean for the value. From number 6 to 10, you remove 3.2, which is the mean for their group. From number 11 to 15, remove 5. That's why you get all those values. Normally, you know, some will be positive, some will be negative. If you try to add it together, it will give you 0. Know that whenever you remove mean from value, mean is a middle value. As much that are higher than the mean are lower than the mean. When you remove mean from the value, some that are equal to the mean, you give you 0. Some that are lower than the mean, it give you negative. Some that are higher than the mean, it will give you positive. So if you had that to, that's all called deviation from the mean. X minus S bar. That deviation from the mean, if you try to add it anywhere, it will give you 0. Because the positive will cancel the negative. That is why intelligent people, what they do is to square it. When they square, if you do column 5, you now square that x minus bar x. When you square it, it removes that negativity. When you square it and remove negativity now, you can add everything together. So what you have, if you look at it now, that column 4 now, 23.6, that is the total variability within the group. But what is the measure of variability is done, but we call it sum of square. Can you see sum of square? So you know x minus x bar, we square it, it becomes x minus x bar square. But it is just sum of, which is sigma x minus x bar square. That's what they just say, sum of square. If you remember, when you calculate variance, what you need to do is that sigma x minus x bar square, you divide by the degree of freedom, n minus 1. It gives you the variance. Square root of variance is standard deviation. So here now, this one gives you the total and the not total, the variance within each group. But we add it together. The variance within group 1, group 2, group 3. The sum of square, rather, the sum of square within group 1, 2, 3, we add everything together. It gives us 23.6. Now, the next column, which is bar x minus bar double x, that double x, that is the grand mean. You know, bar x is the mean of each group. So I told you the second level of variance, I told you variability is that when you try to know the how different each mean is from the grand mean, the variability around the grand mean. So in this situation, how do you do that? You remove the grand mean from each of the group mean. You remember the group mean for group 1, which is number 1 to 5, is 2.2. When you remove the grand mean, we know that is 3.47. When you remove 3.47 for that 2.2, it will give you negative minus 1.27. That's why from number 1 to 5, can you see minus 1.27? Then from number 6 to 10, which is group 2, their own group mean is 3.2. When you remove grand mean, which is 3.47 from it, it will still give you negative minus 0.27. And you see all these 5 minus 0.2. Then you know that the last group, group 3, from 11 to 15, you know the group mean is 5. When you remove grand mean, which is 3.47, of course, it will give you positive now because it's more than the grand mean. So when you remove, it will give you 1.53. That's why all of them are 1.53. So now, of course, if you try to add it as you see, it will give you 0 also. Because those negatives will cancel the positive. So when you square it also, the next column, which is the third to the last column, that next column, when you square that by x minus by double x square, when you square it, you now sum. That is the sum of square between group. Can you see now? The first one, 23.6, is sum of square within group. This one is 20.1335, sum of square between group. The other one is within group, this one between group. The last sum of square, which is the total sum of square, is now inside. You can remove double grand mean, which is double bar x, from the original value. Can you see now? From x itself, not from the mean of whatever. From x, if you remove grand mean from x, that's second to the last column, it will give you this value. When you square it, it gives you, when you add the sum of square, it gives you 43.7335, which is the total sum of square. If you use your distance, just add it. If you have 23.6 plus 20.1335, it will give you 43.7335. That is, the total sum of square is a is addition of sum of square within and the sum of square between. That's sum of square. Now, this sum of square issue, if you have been running regression, you see that, you see this sum of square. You get to know later that regression and ANOVA is the same thing. They are just they are two faces of the same coin. So in those days, the researchers that do experimental research, they like ANOVA because from day one, they will have divided people into try to control for confounder. They have many groups. How many can even have 5, 8, 3, 4, 5 different groups? This one is placebo. This one is this. This one control. This one. This. They just small group. Many in try to remove confounder. They have several groups. They now use ANOVA. Whereas the observational researcher, because they couldn't control for confounder at the design stage, when they run analysis, they use regression to remove confounder. But it's the same. You're going to see in the course of our lecture, maybe it may not be today, I will demonstrate to you that ANOVA and regression is the same. So they didn't know that they actually do the same thing in those days, but later people got online. It's actually the same. Now, let's look at this F-test, this ANOVA, the statistics. So the interest there now is not just this total something now. But we have already said that we want to compare between as the numerator over within as denominator. So this is sum of square, but what we want to compare is the variance. In order to, from the sum of square, the way to calculate variance, I've already told you before, is to divide by the degree of freedom. So if you look at it now, the sum of the variance between, if you want to know the variance between, we serve as the numerator. So that sum of square between, which is 20.1335, you divide by the degree of freedom, which is 2. The degree of freedom is because there are 3 groups, 3 minus 1. So the degree of freedom is 2, 3 minus, because there are 3 groups. You remember how we got it is by looking at difference between the grand mean and each of the 3 groups. So there are 3 groups. So sum of square between over the degree of freedom, which is 2, 3 minus 1. It gives you 10.067. So this is the variance between the groups. So now, you now have just 1 minute